Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we will introduce the ECE 204 course on numerical methods. So in this first topic, we will give a motivation for this course. We will describe the difference between discrete mathematics and calculus, or continuous mathematics, and we will look at the issues of trying to use computers to at least approximate solutions to problems in calculus. To do this, we will then define absolute and relative error. We will describe the decimal and binary representation of numbers. We will define rounding and significant digits, and we will describe the difference between accuracy and precision. We will also then give an overview of the balance of this course. Now, engineering design involves the application of mathematics and science to solve real-world problems, specifically problems where a failure in a design may cause harm to life, health, the environment, or the finances of a client or the public. Now, the real world is modeled through equations and differential equations, and this is a result of conservation laws and other physical laws, the relationship between forces, and the superposition principle. Now, only the most trivial problems can be solved exactly, and no engineer will ever be called on to solve a trivial problem. If a problem can be solved exactly, again, why would anyone pay an engineer to do it? Problems, however, the larger ones, can always be solved using a myriad of different approaches, that is, many different approaches. And seldom is any one approach going to be ideal. So each possible approach will have benefits and drawbacks, and these must be quantified and analyzed. In determining the most appropriate approach, it is often necessary to test the various solutions. For example, how robust is a particular solution? So, for example, if you design a circuit that requires a resistor that is exactly 120 ohms with an error of only plus or minus 0.1 ohms, this is going to be rather expensive. Whereas if your design or solution allows a larger error, whereas still achieving its goals, this would be considered to be more robust. Also, is your solution sensitive to initial conditions? Will small changes to initial conditions result in massively wild, different results? Now, one possible approach to testing your solutions is to build multiple instances of your design and to test them. This, however, tends to be exceptionally costly. And then you also have to determine why a failure, if one occurs, actually did occur. Was it the result of a manufactured issue, or is it an actual issue with your design? Alternatively, if we do have a mathematical description, can we not implement the mathematical description and simulate it? That's what this course is about. So, for example, a circuit is described by Maxwell's equations. This, of course, involves partial differential equations. If we use wires, however, this effectively restricts those partial derivatives into one dimension and therefore results in differential equations and not partial differential equations. If we have differential equations, this is something that can be solved mathematically much more easily. Additionally, it can also be simulated much more easily. Now, the use of linear circuit elements such as capacitors, resistors, inductors, and memristors together with alternating current can further simplify the solutions so that the differential equations end up being represented with algebraic equations. Transistors, as well, can be described linearly according to the conditions of the small signal model. And more complex models can nevertheless still be used and simulated using differential equations. Now, the response of a digital circuit can also be described by a system of linear equations. This can actually involve millions of linear equations in an equal number of unknowns. Solving such a system cannot be done analytically in either a reasonable amount of time or memory. Consequently, we will approximate such systems to find approximate solutions to simulate your solutions. These solutions will use numerical algorithms, as we will see in this course. Now, in your course on discrete mathematics and logic, you were introduced to Boolean logic, set theory, combinatorics, and graph theory. All of these are based on discrete mathematics. In your course on continuous mathematics, or calculus, you were introduced to integration, differentiation, measure, and infinite series. These are what we will approximate and simulate in this course. Now, concepts in discrete mathematics can be modeled using integers, and we implement integers in the computer using data types such as int, long, short, and even unsigned car. Large discrete systems can sometimes more efficiently be approximated using continuous systems. This is something that you will be introduced to in your courses on statistics. Now, in calculus, all the concepts there require real numbers. Hence, as these are the result of limits and other such characteristics of calculus. Real numbers, however, can only be stored approximately. Computers actually use something called floating point numbers, which you were already introduced to in your first year course on programming. Now, interestingly enough, every floating point number actually represents a rational number, not actually a irrational. There are no irrational numbers represented by floats. Every float is a rational number. We consequently approximate all real numbers using only a finite number of rational approximations, and this is going to lead to problems. Now, you'll recall, for example, that the definition of the limit is as follows. The derivative of f at x is a limit as h approaches 0 of the following ratio. We can actually implement the expression on the right-hand side as a function in C++. Here, the parameter f is declared to be a function pointer of a function that takes a double precision number as an argument and returns a double. The parameters x and h are also of type double, and this simply returns the above ratio. We can then call this with, for example, a function pointer to sine as the first argument, with x equaling 1 and h equaling 0.001. Let's try some examples. Here I wrote a very simple function that asks you for the value of x. And then it prints the derivative of sine of x by calculating cosine of x. So that is a reasonable 16-digit approximation of the derivative of sine of x at x equals 1. If we use a value of h equaling 0.1, we don't get a very good approximation of the derivative. Well, 0.497 is not a very good approximation of 0.540, but that's with a value of h as large as 0.1. Let's use a value of h equaling 10 to the negative 5. Now, here you can see that we actually seem to have, when we round to 4 digits, that's pretty close. 5403, yeah, that's pretty close. So we have a more accurate approximation. If we use an even smaller value of h, here 10 to the negative 10, notice that we have even more digits that are correct. So we seem to be doing better and better as h gets smaller and smaller. So in theory, as h becomes very small, we should get a very accurate answer. However, if we let h equal 10 to the negative 15, instead of getting a better answer, we actually get a worse answer. That's not a good approximation. And indeed, if you use 10 to the negative 16, we're now approximating the derivative as being equal to 0, which has about a 100% relative error. So I'm just going to enter 0 to quit. Now, obviously we have an issue here. So what we're going to carry on is look at techniques for describing how good an approximation is as compared to the exact solution. In the next major topic in this course, we will focus on looking at the design of floating point numbers and the issues that come from using this design. Some are beneficial, some have serious problems that we must address while using floating point numbers. The balance of the course will be focused on finding algorithms, specifically numerical algorithms, that avoid the issues with floating point numbers or mitigate the problems of using them. So how good is an approximation? Well, if x approx is an approximation of the value x, we will write that x is approximately equal to this approximation. And therefore, x must be equal to the approximation plus an error term. Consequently, we can always calculate the error epsilon by subtracting the approximation from the exact value. Usually, however, we will refer to the absolute error, which is the absolute value of the difference between the exact value and the approximation. Also, we may sometimes refer to the relative error or the percent relative error. The relative error is simply the ratio between the error and the absolute value of the exact value. The percent relative error is simply the relative error multiplied by 100%. So, for example, from calculus, you already know Taylor series. So f at x plus h is equal to f at x plus the slope at x times h plus an error term. Thus, an approximation of f at x plus h is f at x plus the derivative times h. The error of the approximation is the error term. The absolute error is simply the absolute value of the error term, which can be simplified to a half times the absolute value of the second derivative at some value xi, where xi is some value of x between x and x plus h, all times h squared. Now the relative error, assuming that f at x plus h is not equal to 0, is simply found by dividing the absolute error by the value of the exact answer. Now, you're wondering, if we actually know what the exact answer is, why do we care about the error? Well, throughout this course, what we will do is the following. We will look at our solutions and see how they work with problems where we have the exact solution. We can then see how close the algorithm is for finding the approximate solutions by comparing it with the exact solutions. Consequently, this will give us confidence that the algorithm will work on other problems where we do not actually know what the correct answer is. Now, to begin, it is much easier to discuss absolute error over simply the error. However, neither of these are unit-free, and this can lead to problems. So suppose that you were told that the absolute error of some solution was 10 meters. This is great if you're measuring the distance to the moon. It's a little bit suboptimal if you're measuring the width of a wire. The relative error is unit-free. So consequently, a relative error of 0.01 means that the approximation is good to 1 part in 100 of the actual solution, regardless of the magnitude of the actual solution. A relative error of 0.01 is a 1% relative error. Now, one thing to point out is that the relative error is not defined for approximating 0. But if you're approximating 0 and you know you're approximating 0, then you do have an issue. Note that the Taylor series gives the absolute error and not the relative error in its error term. Next, let us look at decimal representations of real numbers. A non-zero real number can always be written as a decimal number when it is written in the form as we see here. In this representation, we require that D0 is a non-zero digit. Also, each subsequent digit must be some digit between 0 and 9. The exponent e is going to be an integer, and that integer can be positive, 0, or negative. Now, this decimal representation of real numbers is usually contrasted with fractional representations of rational numbers. However, there are also other representations, such as continued fractions, which are nevertheless beyond the scope of this course. Now, if the exponent e is small in magnitude, we may simply move the decimal point. So, for example, if the exponent is 3, we can simply move the decimal point 3 places to the right. If the exponent is negative, we can move the decimal point to the left and add sufficient zeros. So, for example, 1.532 times 10 to the 2 is 153.2. 1.8 times 10 to the negative 3 is just 0.0018. Now, if all digits after some integer n are 0, we will say that this decimal representation is a terminating decimal representation. So, for example, pi does not have a terminating decimal representation, and not even all rational numbers have terminating decimal representations. However, if the denominator of a rational number is, of course in lowest terms, is some product of a power of 2 times another product of a power of 5, then it must have a terminating decimal representation. And of course, vice versa. If a real number has a terminating decimal representation, then it must be a rational number as we just described. Now, if every digit beyond the nth digit in the mantissa is 0, then we will say that this represents an n plus 1 digit decimal number. So, for example, 3.140 is a 4-digit decimal number. 6.62607015 times 10 to the negative 34 is a 9-digit decimal number. All right, that's a review of decimal numbers from secondary school. We're now going to move to binary. Now, a non-zero real number is written as a binary number when it is written in the following form. Here we see that the leading bit must be non-zero, but there's only one leading non-zero bit, and that is 1. Every other bit or binary digit in the mantissa is either 0 or 1. The exponent e is going to be an integer again. Now, normally the base and the exponent are written using decimal numbers. If the exponent e is sufficiently small in magnitude, we may simply move the radix point. So, for example, if this binary is multiplied by 2 to the 3, we may simply move the radix point 3 spaces to the right. And if it's multiplied by 2 to the negative 4, we may move the radix point 4 places to the left, padding with an appropriate number of zeros. So, for example, this binary number times 2 to the 3 is the same as 1001.101. And this second number times 2 to the negative 2 is the same as 0.0110011. Now, looking at those two numbers, sometimes it may be questionable. Does that represent a binary number or a decimal number? If there is ambiguity, we will sometimes add a subscript 2 to emphasize that this is a binary representation. We can also use the convention from C++, where we prefixed the number with a 0b. Now, if all bits after the nth bit of the mantissa are all 0, we will then say that this binary number has a terminating binary representation. And consequently, this indicates that this number represents a rational number with a denominator of some power of 2. Now, if the representation of a number has all bits after the nth bit being 0, we will say that this represents an n+1 bit binary number. So, for example, 1.010 is a 4-bit binary number, whereas this number here is a 15-bit binary number. Now, most real numbers have infinitely many digits when written in either decimal or binary representations. This, of course, would theoretically require an infinite number of digits to store, but we don't have that much memory, and we never will. Not only that, even the real numbers that have terminating representations have far more digits than we care about. So, for example, here we see 51 digits approximating the value of pi. As an engineer, it is very unlikely that you will ever require 51 digits in any calculation when you are simulating some real-world phenomena. So we can't store an infinite number of digits, and memory is not free. We can't even store that many digits, be they decimal digits or binary digits or bits. In fact, the most efficient means of implementing decimal and binary representations of numbers is to simply store a fixed number of digits. So we will need to represent all real numbers by a decimal or binary number that has a fixed number of n digits in the mantissa, be those n digits decimal digits or binary digits or bits. So which n+1 digit number, that is, with n digits in the mantissa, do we use to approximate any given real number? Well, what we'd really like to do is find that n+1 digit number that has the smallest absolute error when compared to the actual number we are attempting to approximate. We will say that we are rounding a real number x to the closest n+1 digit decimal or binary number. The rules for decimal rounding are as follows. To round a decimal representation to n+1 digits, if the next digit is 0 through 4, we simply truncate all subsequent digits. If the next digit is 5 through 9, but all subsequent digits are not exactly 5 with an infinite number of zeros thereafter, we will truncate all subsequent digits and increment that last remaining digit, d sub n, by 1, and that of course may result in a carry, which we will then perform. So, For example, let us round 1.534982 to 3 digits. Well, that next digit is a 4, so we simply truncate all subsequent digits, leaving us with 1.53. Rounding this to 4 digits, we note the next digit is a 9, and thus we truncate, but we add 1 to 4, resulting in 1.535. Rounding to 5 digits, we note the next digit is an 8, and thus we truncate and add 1 to the digit 9. This, of course, causes a carry, which we calculate through, resulting in 1.5350. Finally, truncating or rounding to 6 digits, the next digit is a 2, and thus we simply truncate to 1.53498. The rules for binary rounding are as follows. If we want to round this number in binary representation to n plus 1 bits, including that leading bit, if the next bit is 0, we just truncate all subsequent bits. If the next bit is 1, but all following bits are not all 0, so if even one bit following that last one is not 0, we will then drop all subsequent bits, but we will add 1 to the last remaining bit, and again this may result in a carry. So, for example, to round this number to 3 bits, we note that the next bit is 1, and it is not 1 followed by an infinite number of zeros, and therefore we add 1 to the last remaining bit, the third bit, and that produces 1.111. If we want to round that number to 4 bits, again, we examine that next bit. It is 1, and all subsequent bits are not all 0, and therefore we increment the last remaining bit after we've truncated, and that does, in this case, cause a carry. And so, rounded, it is 1.110. To round it to 5 bits, the next bit is 0, so we simply truncate, leaving us with 1.1011. And to round to 6 bits, again, we have 1, but not all subsequent bits are 0. Therefore, we increment the 6th bit, which results in 1.10111. Now we skipped 2 cases. For the decimal numbers, when rounding, we skip the case when the next digit is 5 and all subsequent digits are 0. And in the binary case, we skip the case where the next bit is 1 and all subsequent bits are 0. We skip this because these two numbers are exactly halfway in between two n plus 1 digit numbers. And thus, there are two numbers that have the same absolute error in approximating these two values here. So the question is, do we round up or round down? If we choose only one of these two options, we actually will start to introduce a bias into our calculation. So if we only round down, if we are performing thousands and thousands and perhaps even millions of calculations, this will give us a slightly smaller number than on average. If we round up, then our results will be biased to a larger value. Instead, what we're going to do is we will choose one 50% of the time and the other 50% of the time. So the rules are as follows. In the above case, for decimal rounding, if the next digit is 5 and all subsequent digits are 0, then we look at d sub n. If it is odd, we increment it. Otherwise, we simply truncate. For binary, if the bit b sub n is odd, and of course there's only one odd bit, we increment it. Otherwise, once again, we leave it. And again, when we increment, this may result in a carry. Now note, we've only discussed rounding in the context of our formal representation of decimal and binary numbers. If, however, we have a decimal or binary number where the radix has been shifted either to the left or to the right, leaving off the times 10 to an exponent or times 2 to an exponent, if we are rounding, we will simply start counting digits at the most significant digit. So to round this to 4 digits, we start at 5838. The fifth digit is 1, therefore we truncate. For this number, if we round it to 3 digits, we go to the fourth digit, which is 5. All subsequent digits are not all 0, so we simply truncate, but then increment the digit 8, leaving us with 109,000. Now, with the trailing zeros, it's still not clear that we've performed a rounding here. So it's a lot clearer if we are rounding that we would represent it as 1.09 times 10 to the 5. For this number here, if we are to round it to 5 binary digits or 5 bits, we observe that the sixth bit after the first leading 1 is a 1, and all subsequent bits are not all 0, so we truncate the 101 and increment the last bit. Rounding this to 4 bits, we note that the fifth bit is 0, and so therefore we simply truncate all remaining bits, which leaves us with this number here. Once again, it's not clear that this number has been rounded, so it makes more sense to represent it as 1.110 times 2 to the 8. Another colloquial means of describing the relative error of an approximation is to use the concept of significant digits. Now, we are not going to calculate this explicitly ever. It's a very coarse approximation, and we will only use such terminology colloquially when trying to describe how good an answer is, at least approximately. So instead, we will only use the number of significant digits to give a rough estimate as to the relative error. For example, one significant digit indicates that the relative error is no greater than 50%. Two significant digits indicates the relative error is no greater than 5%, and so on and so forth. However, a rough approximation of the number of significant digits is as follows. An approximation approximates an exact value x to d significant digits if both x and the approximation rounded to d digits agree in all those digits. Now, this is not exact, but it's a good rough approximation of what the significance of the number of significant digits is. Now note, from the definition, we can find a formula to calculate the number of significant digits given the relative error. So if we have the relative error, and this must be less than or equal to 5 times 10 to the negative d, if we want to find d, well, let's divide both sides by 5, which is positive. We can now take the common logarithm of both sides, log base 10. Now, if the left-hand side is less than or equal to negative d, but we want it to be as close as possible, we can take the ceiling of both of that left-hand side, and then we can bring the negative sign to the other side, giving us that d is equal to this expression. So once again, we could in theory calculate the number of significant digits precisely, but we will only use significant digits really to colloquially describe how good an approximation is. If we actually want to discuss the relative error, we will then present the exact relative or, if appropriate, absolute error. Now, let's discuss these errors with respect to an approximation that's quite ancient. The Babylonians were aware that if x is less than the square root of 2, then 2 divided by x must be greater than the square root of 2. Of course, if x is equal to the square root of 2, then 2 over x is also equal to the square root of 2. While if x is greater than the square root of 2, then 2 over x must be less than the square root of 2. Consequently, x and 2 over x must be on opposite sides of the square root of 2. Thus, if x approximates the square root of 2, it follows that the average of x and 2 divided by x must be a better approximation of the square root of 2. So therefore, here's the average, and this gives us a formula to find a better approximation of the square root of 2. All right, let's look at the application of this formula. 1, as an approximation of the square root of 2, has an absolute error of just slightly less than 0.5. Its relative error is therefore 0.2929, and it has a 29% relative error. It also has one significant digit. If we apply the formula 1 plus 2 divided by 1, all divided by 2, that gives us 1.5 as the next approximation of the square root of 2. It has a smaller relative absolute error, consequently a smaller relative error, and that the percent relative error is approximately 6%. Again, we still have only one significant digit. With one more iteration, so 1.5 plus 2 divided by 1.5, all divided by 2, so the average of those two, that gives us this next approximation. The absolute error is again becoming smaller, as is now the relative error, and so now we have a relative error less than 1%. We also have 3 significant digits. If we take one more iteration, taking 1.416666 plus 2 over that and take the average of those two, we get this approximation here. Note the absolute error is becoming very small indeed, and so now we have 6 significant digits in this approximation. Now note, in this course, we will always round the absolute error or the relative error to 4 digits when presenting this information. We could use fewer, but later it will be useful to see 3 or 4 digits in the absolute and relative errors. We're going to introduce 2 more concepts, precision and accuracy. Now, the concepts of precision and accuracy are usually introduced in all textbooks with respect to target practice. The Tikka T3X TAC-A1 is a much more precise firearm than the AK-47. So suppose we take these 2 firearms to the range. If I am trying to hit a target at 100 meters, the Tikka will be much more precise than the AK-47. Now, if someone else who's a less experienced shooter uses these firearms, the precision will be reduced. But nevertheless, even a novice will have a better grouping or be more precise with the Tikka than with the AK. Now, suppose instead we take both firearms but introduce an error into the sights. The Tikka will still be precise, but it will not be an accurate grouping. We are no longer near the bullseye. Similarly, the AK will be both imprecise and inaccurate if an error is introduced into those sights. Now, when we are solving problems numerically, we're going to have a plethora of different algorithms we could consider using. We will describe each algorithm in relationship to the others via their relative accuracy and their relative precision. Now, in general, all of our algorithms are going to be parameterized by at least one value. For example, an algorithm may be parameterized by a value h that may be made arbitrarily small, and hopefully as h becomes smaller, the precision becomes better. And hopefully, if the algorithm is correctly written, we will also get an accurate answer that is also precise as h becomes smaller. We may also be able to parameterize an algorithm with some integer n that may be made arbitrarily large. And again, as n is made larger, hopefully the algorithm will become, once again, more precise and more accurate. So, in approximating a solution X, an algorithm is accurate if, as we adjust our parameters, the absolute error of our approximation is correspondingly reduced. One algorithm will be more precise than another if the absolute error of the first algorithm is generally less than the absolute error of the second, assuming accuracy. All right, to look at an algorithm that allows us to compare accuracy and precision, suppose you have a sensor you're reading and you're reading that sensor 4 times. Each time you know that the sensor is going to produce a random value that is uniformly distributed between A and B, but you don't know what the values of A and B are. So you might take 3 readings, 5.7, 3.2, 8.5, 6.3. Can we estimate the values of A and B? So what might be a good approximation of A? Well, given the numbers I just previously said, chances are A is not negative 55. Similarly, B is likely not 783. B is definitely not 0 because all of the values or the readings we got were greater than 0. So what might be a good approximation of A? Well, you could just take the minimum of these 4 readings. Is that a good approximation? Well, chances are if you're uniformly returning a value between A and B, you're probably not going to return exactly A. You're going to return something, you might on occasion return something close to A, but the minimum of these 4 readings is likely not going to be equal to A. Actually, you can show statistically that this is the minimum of these 4 is actually not a bad estimator of this ratio 4A plus B over 5, which is just A plus a little bit. Similarly, the maximum of those 4 readings you made is actually a good approximation of B minus B over A over 5. Okay, so that you will see in a course in statistics, but I'm just going to give you that statement now. The minimum of 4 readings is a good approximation of the first expression. The maximum is a good approximation of the second. That is, these are accurate approximations of these 2 values. However, both of these now give us 2 equations. So if we multiply both sides by 5, we have these 2 equations. Well, this now gives us 2 linear equations in 2 unknowns. And of course, from linear algebra, you know that you can solve for A and B. So solving for A and B, we actually get that if we want a good or a more accurate approximation of A, we will take the minimum of the 4 readings, multiply it by 4, subtract off of it the maximum of the 4 readings, and then divide by 3. This is actually a more accurate approximation of A than is simply taking the minimum of the 4 readings. The same for the approximation of B. Consequently, if we are reading a sensor that is known to return values uniformly between 2 extremes A and B, but we don't know what A and B are, then taking 4 readings and finding the minimum of them, that is a less accurate approximation of the left-hand boundary than is this more complex formula. So the second is more accurate. Now, the mathematics is beyond the scope of this course, but interestingly enough, the precision of the first approximation is actually better than the second. That is, the standard deviation of the minimum of 4 values is smaller than the standard deviation of the more complex expression. Now, suppose in this example we are uniformly sampling from a sensor that returns a value between 5 and 25, but we don't know what those bounds are. Instead, all we can do is read the sensor. We could take, instead of 4 readings, take 10. All right, now with these 10 readings, the minimum of these is 8. Well, 8 is an okay approximation to 5. It gives us approximately what the lower bound is from which these readings come. We could instead increase it to 20 readings. Here are 20 readings. Now, if we take the minimum of these, which is 5.4, that is a more accurate approximation of the lower bound 5. So, as the number of samples we take becomes larger, it seems the minimum of the samples that we do take becomes a better and more accurate approximation of the lower bound 5. Now, we can modify the other formula to deal with the fact that we have more samples. So now, we could approximate the lower bound A by taking the minimum of n samples, or we could calculate the following linear combination of both the minimum and the maximum of the sample. Now, the second formula is just as easy to calculate as the first, more or less. You're finding the minimum of the n samples, the maximum. So that one should be slightly better. So looking at our previous examples, when we sampled it 10 times, the minimum of those values was 8. If we take 10 times 8 minus the maximum in the 10 samples, divide all of that by 9, we get 6.8. 6.8 is a better approximation of the lower bound 5 than the original minimum. Still not a great one, but better. When we took 20 samples, the minimum of the 20 samples was 5.4. This is a better approximation of the lower bound 5, because again, remember, even though I generated the data to be uniformly sampled from 5 to 25, once I have the data, I'd like to see whether or not I can determine what the lower bound was. So now 5.4 is a better approximation of that lower bound. If we substitute both the minimum and maximum into this formula, we get a different approximation of the lower bound. Now we're overshooting the lower bound. We're at 4.379. And oddly enough, that's actually not as good an approximation as 5.4 is. The absolute error of 5.4 was 0.4. The absolute error of this second approximation is actually slightly larger than 0.6. So we're not guaranteed that the error will always be better with a more precise or more accurate formula. It's just on average it will be better. But in this case it happened that for this particular sample that was not the case. All right, so given n samples from an interval AB that are uniformly distributed, that means every single point in the interval from A to B has an equal chance of being returned, the minimum of those n samples is not as accurate as our linear combination of the minimum and maximum is in approximating the value of A. However, the minimum of n samples is more precise than our linear combination in approximating A. That is, the values tend to be closer to each other. It's giving you the wrong answer, but they are more precise. As we increase n, both formulas become more precise. Now, you don't have to know these formulas for this course. I came up with this example to demonstrate the difference between accuracy and precision. You can try this yourself. Suppose I have a different interval a, b, and I have 5 samples from that interval. All right, so here are 5 samples. How would you estimate the lower bound of the interval from which these 5 samples are taken? Similarly, if you had these 10 samples, how would you estimate the lower bound from which these 10 samples were taken? Pause the video, try it yourself, and when you come back, I'll give you the interval from which they came. Welcome back. These were uniformly sampled from the interval -6.3 to -1.3. As you can see, none of the values were less than -6.3 and none of the values were greater than -1.3, but none of the values were equal to either of those endpoints either, although -6.28 was quite close. So the next topic in this course is going to look at floating point numbers. Floating point numbers only approximate real numbers, and so while they're very fast and efficient, they will have issues with them. So we will be looking at the issues with floating point numbers, and thus throughout the balance of the course we will make sure that we use techniques to avoid the problems posed by using floating point numbers. As you'll recall, we could not even precisely approximate the derivative of a function using floating point numbers, even though the formula says it should be correct. The formula said that the limit of f at x plus h minus f at x all over h should approximate the derivative, and yet as we made h smaller and smaller, the precision increased to the point that we had maybe 5 significant digits, but then as h became even smaller, the precision went away. So we will be looking at the issues with floating point numbers. Following this, the balance of the course will be looking at numerical algorithms to solve topics in one of 4 categories. We will be evaluating expressions to a numeric value. For example, we may want to evaluate a polynomial at a point. We may want to estimate a derivative or an integral. All of these are the same type of problem. All of these will involve either interpolating polynomials or the use of least squares. We will then go on to solve algebraic equations and systems of algebraic equations. This will include systems of linear equations, but we will also be looking at nonlinear equations and systems of nonlinear equations. Next, we will look at finding approximations to solutions of analytic equations and systems of analytic equations. Specifically for engineers, this includes differential equations and systems of differential equations. Finally, we will look at optimizations, maximizing functions that take a real value, that return or evaluate to a real value. Well, maximizing or minimizing. Following this topic, you now understand, at least at a high level, the purpose of this course. You are aware of the differences between discrete mathematics and continuous mathematics or calculus, and you've observed that floating point numbers do cause issues when trying to approximate solutions in continuous mathematics or calculus. You know the ideas behind absolute and relative errors, the decimal and binary representations of numbers, the ideas of rounding and significant digits, and you understand the concepts of accuracy and precision. You also have an overview of what will be covered in the upcoming lectures and the balance of this course. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!